right. How you doing, Sam?
Good. How about you?
The EEs is 70 to 96%, and then percent yield 56 to 99%, which is great. And even though it's 20% catalyst, that's decent for an organocatalytic reaction. Again, the gold standard is 1% catalyst or 0.5% catalyst. If you can get that low, which is phenomenal, but at the same time, 20% is not horrible, and it's not stoichiometric, so that's good. But you can see even with these conjugate additions, there's a chance to build up some really unique architectures, some unique structures um, with this catalyst, right? So you can see here, especially with this particular molecule here, where you set this stereo center. If your alpha beta unsaturated carbonyl is substituted at the beta site, you're able to set a stereo center here. You can see it's 89 to 99% EE, which is excellent. Um, and then down here, you can even do like a derivative of what's called a Henry reaction, where you take a nitrate as your electrophile. You can see right here, you can add that in a conjugate fashion. In this case, is acting as a nucleophile, but the outcome, the product is similar to what we would see in a Henry reaction. But here again, 89 to 98% EE, and then 80 to 97% yield. So this is the catalyst, the alkaloid catalyst right here. And you can see that, it is one of those, what you call an activated catalyst. You have your nitrogen has a positive charge on it. And so that makes that the Lewis acidic portion of the catalyst. And the way they claim that it works is like this. So with the nitrogen having a plus charge, the and acting as a Lewis acid, right? The carbonyl can coordinate with that with the lone pairs on oxygen, and that you can see again the kind of the cavity that's created by the catalyst right here. So the nucleophile is either going to come in from one side or the other to do that 1,4 addition, right? So you end up with these two possibilities, these two products, and then when you just protonate it, quench it with acid, right? You get a beta substituted carbonyl, right? It's almost similar to the aldol in the sense that your final product is like a beta substituted carbonyl, but the aldol addition doesn't happen or the condensation doesn't happen. You basically start with kind of like almost like a aldol condensation product, and then in uh, adding a nucleophile to it, you got access to both of these enantiomers. What I don't recall is whether or not there's another version of this catalyst that could favor the opposite enantiomer. I think it's all based on just the Lewis acid Lewis base interaction between the starting material and the catalyst, right? But you can see again, you see a nice cavity formed here, so that nucleophile is going to prefer to attack from either one face or the other, because with the alpha beta unsaturated carbonyl, this double bond is planar, and so when you attack a double bond, you don't necessarily attack it from a how do I want to put this? Since this sp2 is going to be planar, so you're going to have it'll be facial selectivity, where the nucleophile can either attack from the top face or from the bottom face. And especially since it's conjugated, that's also going to help to hold it in that planar conformation. All right. So the other way to induce chirality is through resolution, right? We've talked about asymmetric catalysis. We've talked about using chiral auxiliaries. We talked about organocatalysts. And now the other way to induce chirality is to use what's called resolution, right? Now, there are a lot of different methods, but resolution is basically separating out stereoisomers based on their chemical or physical properties. All right. So how it works You can use chromatography to do it. You use HPLC or GC to separate out the enantiomers, and you basically take a racemic mixture, right? So here you got both enantiomers, and this is highly simplified just to make the point. And then you pass both enantiomers over a chiral stationary phase, like a column, right? And that stationary phase is going to match with one of those enantiomers, and it's going to be mismatched with the other enantiomer because the stationary phase doesn't change, right? And you can see right here, this is mismatched. And no matter how you turn this, you're not going to be able to align this enantiomer with that stationary phase. So the mismatched one doesn't stick, right? It's going to fly through that column and come out first. And then the matched enantiomer does stick. And so it doesn't come out as fast. So when you see the chromatogram, what you'll notice, and let me do this right quick because I'm not sure if you've seen this or not. So I need to should have already had that in here, but let me pull up let me pull up a chromatogram and show you what I'm talking about. All right, so let's say you have a chromatogram that looks like this, right? On that x-axis, that's your retention time. So that's how long it takes that species to elute from the column. And you can the good thing about HPLC is that you can actually watch this grow in, right? And if your isomers are spaced out enough, then that's even better because that way, if you need to collect them, especially if you're doing HPLC, liquid chromatography, you can open up one end of the column, and when you see the trace growing in, like so, you can actually take that uh, eluent, collect it. You can see here if you start at 2.5 and go to, I guess that might be around 3.5, 3.5 minutes. If you take that, you can actually collect that eluent and collect that fraction. And you can do the same thing with this and here, as well as here, right? So the retention time matters, right? When you're trying to do resolution using a column, using a chiral column, you can pass the enantiomers over it, and as they elute, you can actually collect the fractions. So here, this is one fraction, this is another fraction, this is another fraction, so on and so forth. So these, let's say these two right here are your two enantiomers, right? At about say about 5 minutes and about 6.5 minutes, right? If those two are it has it right here, 5.422 minutes and then 6.7 minutes. So if those two are your enantiomers, you can actually collect them, right? The one that comes out at 5 minutes is going to be mismatched because it comes out faster. The one that comes out at 6.7 minutes is going to be matched because it comes out slower. So again, that's how you can. That's a way you can use chromatography or chromatographic methods to actually separate out and resolve enantiomers, right? So here you can again open the end of the column, collect the fractions. The technology is probably to the point now where you don't have to do that. It'll collect them for you, right? I'm not current on that on the current chromatographic resolution methods. I need to bone up on that, but the point is you can collect fractions and resolve those enantiomers and collect them separately, right? Because again, you can't separate enantiomers using flash chromatography, which we talked about the other day, but you can definitely collect diastereomers using flash because they're physically separable. So let me go back to here. All right. So this is one way to do resolution, right? Uh, so again, you can use HPLC, you can use GC. I'm not certain if you can use supercritical fluid chromatography to do that, unless you have a like a special uh, attachment where you're able to collect those fractions. Um, but yeah, you can definitely use this as a resolving method. You can also use what's called a chiral derivatizing agent, and I've actually used this before myself. The way that you tell the two diastereomers apart is by NMR. You can take an NMR and you can tell uh, the diastereomers apart, and that's how you know that you have them, and that's how you know that you can separate them, right? So right here you have an enantiomerically pure species, but if you esterify that acid using DCC, DMAP, and dichloromethane room temperature, once you esterify that, right, you get these two diastereomers, right, because this stereo center is different here and here, right? You take, so this is your mixture of enantiomers, this is your derivatizing reagent, so you esterify both enantiomers, right? And you get these two diastereomers. Then you can separate those out. Again, you can separate diastereomers out on a column, right? As long as you can see them on silica gel, and you can run do flash chromatography, get them to dissolve up, get them onto a column, you can separate them with no problem. So these chiral derivatizing agents are very useful for separating out enantiomers, because again, there's no way to separate them physically other than derivatizing them or using some type of chromatographic method other than flash chromatography, right? So you can just separate those easily. And what you do is, again, if you have a racemic mixture, you add in this derivatizing agent, and it converts each one of the enantiomers in that mixture into diastereomers. Right. One other method is to use what's called enzymatic resolution. Right. So uh, lipases are very popular for doing this, and the reason for that is enzymes are very compound specific. Right. Very selective. Uh, and so the enzyme itself, like in this particular case, the way this works is, here's your substrate that you're trying to resolve. You have both R and S. So the fluorine, obviously, these are your two isomers here. All right. Uh, so you take that, you add it to this solution containing this lipase enzyme from Pseudomonas cepacia, and it's a 60% conversion. And in this case, you have the way that these are resolved is one of them ends up in the organic phase, and one of them ends up in the aqueous phase, right after after your workup. So again, how this works, the enzyme itself is specific, right? It has a pocket, basically it's a like a donor receptor type relationship. So within that enzyme, there's some functional group that's going to uh, bind to your substrate in some type of way. For this, it's going to actually bind to the sigma star orbital of the carbon fluorine bond, right? Because there's no other Lewis acidic atoms here or species here other than the carbonyl that could bind to. But in this specific case, it binds to the sigma star orbital uh, of the fluorine carbon bond, right? And the way this works is, again, once that binds, it's specific uh, for the R enantiomer. So it binds the R specifically, and then it leaves behind the S. Again, one of the drawbacks of doing resolution is the fact that if you do resolution, sometimes you end up trashing one of your enantiomers. And that's not always good unless you just don't care. But if you got a highly complicated system that you synthesize, then you do care, and it does matter. All right. Uh, so again, this is one method for resolution, right? Here over here, this is another kind of a method that's plausible, and you can see this does actually interact with the carbonyl carbon, right? But this is the enzymatic method. Here is the method that actually is used for um, the resolution of these two enantiomers. All right. You got any questions about anything?
No, sir, not right now.
All right. Rather than start another topic, I need to look at um, the syllabus real quick to make sure I know where we're going next. So I'm gonna stop recording and